Today we're going to be presenting on our project, which was the aerodynamic analysis of a Lamborghini Aventador. So before we get into the technical aspects of the project, we're going to discuss the purpose. So when deciding the direction for our project, the question we ask ourselves is, why does this matter? Cars have transformed how we live in the modern world, whether it's a long-distance road trip or a simple commute to Bush campus. Yet most drivers, including myself, don't really know much about how their vehicle performs beyond things like miles per gallon. I drive a Honda CR-V, which is on the slide right now, but I couldn't tell you how it compares aerodynamically or economically to an Acura MDX or a Volvo XC90, for example. Our project dives into one of the lesser known but critical factors behind fuel efficiency, which is aerodynamic drag. By simulating airflow over a 2D profile of the Lamborghini Aventador, we explored how vehicle shape affects resistance from air, something every car experiences in real-world motion. Although we didn't capture the more complex behaviors that you find in 3D models, the patterns and trends that we observed in the 2D case should still hold for practical applications. The goal isn't just to analyze a supercar, but to understand how the different design features on the car, like sharp edges or curves, influence your performance. So these principles apply to everyday cars too. For instance, the picture we have here depicts the effect of rolling down your windows and how it increases drag, which forces your engine to work harder and burn more fuel. On a hot day, would people use the air conditioning system instead if they knew this? We can't say that for sure, because a lot of people in the summers still tend to roll their windows down. But knowledge is power in this situation. So this study aims to give drivers a better understanding of what they drive, and whether you're buying a new car or just curious about your daily commute, our findings offer a clear picture of how form and the different aspects of a car body impact its function, and how making smarter designs can lead to savings and efficiency. While we use powerful software like ANSYS Fluent to run our simulations, what matters most is the following idea. Anyone can start exploring how a car's shape interacts with the air around it. You don't need to be an expert. We're just engineering students with limited simulation experience. With some curiosity, you can also investigate the factors that affect vehicle performance. Now with that, we're going to transition into the technical details of our project.
So on to our technical details. To explore the aerodynamic performance of high-speed vehicles, we simulated airflow over a 2D side profile of the Lamborghini Aventador. We chose this vehicle due to its publicly available specifications and iconic streamlined shape. This gives us a solid foundation for building accurate and scalable results. We ran our simulations using ANSYS Fluent, applying the Reynolds average Navier-Stokes equations with a K-omega turbulence model. To reduce the complexity while still capturing meaningful aerodynamic behavior, we limited the flow to the longitudinal direction and analyzed a 2D cross-section. We used a rectangular domain and excluded underbody flow, focusing solely on the upper body's interaction with air, which is similar to a wind tunnel test. To ensure our simulation was both accurate and efficient, we performed a mesh geometry and a time-step convergence study. And for our mesh study, we found that a mesh size of 0.25 millimeters struck the right balance, giving us a consistent drag result within a 0.53% compared to the finer meshes without unnecessary computational cost. And for our main test here, we tested 4 different primary cases, one being a flat rectangular shape, second being a linearized Aventador profile, a realistic profile, and the last one being a linearized model with a rear-mounted bike rack. And these were all tested at a cruise speed of 13.86 meters per second. And from our simulations, it was found that the realistic body had the lowest drag at 54.77 newtons. And also the linearized version showed nearly triple the drag, confirming the importance of curvature in reducing aerodynamic resistance. And also the bike rack had a minimal drag impact in 2D. As you can see here, very minimal difference there between the two. But this would likely change in a 3D model. And finally, by visualizing the turbulence contours that we saw on the last slide, and also the streamlined contours that you can see here, we saw how the eddy viscosity models form flow separation for the different geometries, and how the impact of recirculation at sharp edges occurred. You can see that very vividly here in the top picture here, where at the sharp edges of the bike rack there's a lot of circulation. And also the streamlined bodies shed vortices farther away, which reduces pressure buildup and drag. And now for our closing remarks, as mentioned earlier, the realistic model had the lowest drag, while others vary due to different geometries. And also for future work, we could include 3D flow modeling, underbody interaction, transient startup analysis, and structural vibration studies. Our findings demonstrate how simplified simulations can still offer meaningful insights and show how design choices directly affect performance. And as our project, thank you so much.